The James Webb Space Telescope unveils how tiny galaxies built the universe. Hello everyone, welcome back to our channel. In today's video we will dive into the topic that explore the James Webb Space Telescope, JWST, with its unprecedented sensitivity and advanced technology, has opened a new chapter in our understanding of the cosmos. Among its most groundbreaking findings is the critical role that tiny galaxies played in shaping the universe during its formative years. By shedding light on these faint and diminutive structures, JWST has provided key insights into the epoch of ionization, galaxy evolution, and the larger-scale structure of the universe. This essay delves into the significance of these discoveries, exploring how tiny galaxies contributed to the universe's evolution and the broader implications for astrophysics. The epoch of ionization, a turning point in cosmic history. The story begins approximately 13 billion years ago, during a period known as the epoch of ionization. After the Big Bang, the universe was a dark expanse filled with neutral hydrogen gas. This state persisted until the first stars and galaxies formed, emitting light that ionized the surrounding hydrogen and transformed the universe into the transparent, light-filled expanse we observe today. Ionization marks a pivotal phase in the universe's history, a transition from darkness to light. However, the precise mechanisms driving this process have long eluded scientists. The primary suspects have been galaxies, with larger and brighter galaxies receiving the bulk of attention. JWST has changed this narrative by identifying the outsized impact of tiny galaxies in this era. Tiny galaxies, the unsung heroes of ionization. What are tiny galaxies? Tiny galaxies are small, faint structures that are often less than 1% the size of the Milky Way. Despite their diminutive nature, they were abundant in the early universe, forming hundreds of millions of years after the Big Bang. Unlike larger galaxies, these systems are characterized by low mass. Their total mass, including stars, gas, and dark matter, is relatively small. High star formation rates. Despite their size, these galaxies often experienced intense periods of star formation. Low metallicity. Because they form so early, tiny galaxies contain fewer heavy elements, which are produced by successive generations of stars. How tiny galaxies contributed to ionization. JWST's advanced instruments have provided direct evidence that tiny galaxies were major contributors to ionization. Key aspects of their impact include high ultraviolet output. Tiny galaxies were surprisingly efficient producers of high-energy ultraviolet (UV) light. This light is crucial for ionizing hydrogen, breaking the atom into protons and electrons. Escape of ionizing photons. Unlike many larger galaxies, which often trap UV radiation within dense clouds of gas and dust, tiny galaxies allowed a significant fraction of these photons to escape into the intergalactic medium. Sheer numbers. While individually faint, the sheer number of tiny galaxies made the cumulative contribution to ionization greater than that of larger galaxies. These findings underscore the critical role of tiny galaxies in one of the most transformative periods of cosmic history. JWST's technological edge. The ability to detect and study tiny galaxies owes much to JWST's cutting-edge technology, particularly its infrared capabilities. Because the light from distant galaxies is red-shifted, stretched to longer wavelengths as it travels through the expanding universe, infrared observation is essential for studying the early universe. JWST's instruments, such as the Near-Infrared Camera (NIR-CAM) and the Near-Infrared Spectrograph (NIR-SPEC), are uniquely equipped to detect faint objects that were previously invisible to telescopes like Hubble. Measure the spectral properties of light, revealing information about a galaxy's composition, age, and star formation activity. Map the distribution of galaxies during the epoch of ionization, offering insights into the large-scale structure of the universe. The life cycle of tiny galaxies. Formation and evolution. Tiny galaxies formed in regions where dark matter had clumped together, creating gravitational wells that attracted gas. These early galaxies likely experienced rapid bursts of star formation fueled by the cooling and condensation of hydrogen gas. Over time, feedback processes such as supernovae explosions could have temporarily halted star formation, dispersing gas and limiting the growth of these galaxies. However, their compact size and relatively simple structure allowed many to recover and continue forming stars. Mergers and growth. As the universe aged, tiny galaxies often merged to form larger structures. This process of hierarchical assembly is a cornerstone of modern cosmological models. By studying these mergers, JWST has revealed how tiny galaxies acted as the building blocks of more massive galaxies, including those we see in the present-day universe. Clues from spectroscopic analysis has been pivotal in understanding the properties of tiny galaxies. JWST's instruments can break light into its constituent wavelengths, providing a wealth of information about these objects. Key findings include metallicity. The low levels of heavy elements in tiny galaxies confirm their status as some of the first structures to form in the universe. Star formation rates. Spectra reveal the presence of young, massive stars, which are short-lived but highly efficient producers of UV radiation. Ionization conditions. The intensity and characteristics of emission lines indicate the conditions under which photons escaped, helping scientists model the ionization process. The cosmic web and large-scale implications. The discovery of the role of tiny galaxies has significant implications for understanding the universe's large-scale structure. Tiny galaxies were not isolated entities. They existed within the cosmic web, a vast network of dark matter and gas that provides the framework for galaxy formation. Seeding larger structures, tiny galaxies were instrumental in shaping this web. Their gravitational influence helped funnel gas into filaments, creating regions of higher density where larger galaxies could eventually form. Chemical enrichment. As stars within tiny galaxies burned and exploded as supernovae, they released heavy elements into the intergalactic medium. This process of chemical enrichment seeded the gas that would later form stars and planets, including those in our own solar system. Challenges and open questions. While JWST's findings have revolutionized our understanding of tiny galaxies, they have also raised new questions. Photon escape mechanisms. What specific physical conditions enabled such a high fraction of UV photons to escape these galaxies? Undetected populations. Are there even fainter galaxies that JWST cannot detect, and what role did they play? Impact of feedback. How did processes like supernovae explosions and stellar winds influence the evolution of tiny galaxies? Implications for cosmology and astrophysics. Dark matter. The formation of tiny galaxies is closely tied to the distribution of dark matter. By studying these galaxies, scientists can refine models of dark matter behavior and its influence on cosmic evolution. Galaxy formation models. JWST's observations challenge existing models of galaxy formation, particularly those that underestimate the importance of small-scale structures. This has led to a re-evaluation of the processes driving early star formation and galaxy assembly. Planetary systems and life. The heavy elements produced by tiny galaxies played a crucial role in forming planets and, by extension, the conditions necessary for life. Understanding the chemical enrichment of the early universe provides context for the emergence of habitable environments. Future directions. JWST's journey is just beginning. Its continued observations will expand our understanding of tiny galaxies and their role in the universe's evolution. Upcoming projects include gravitational lensing studies, using massive galaxy clusters as natural magnifying glasses to detect even fainter galaxies. Deep field surveys, extended observations of specific regions of the sky to identify the smallest and most distant galaxies. Collaboration with other observatories, combining JWST data with observations from telescopes like the Vera Rubin Observatory and the Square Kilometre Array to create a comprehensive picture of cosmic evolution. Conclusion. The James Webb Space Telescope has fundamentally reshaped our understanding of how the universe evolved, highlighting the profound impact of tiny galaxies. These unassuming structures were instrumental in ionizing the universe, enriching the intergalactic medium with heavy elements, and laying the groundwork for larger cosmic structures. By uncovering the hidden influence of tiny galaxies, JWST has demonstrated that even the smallest components of the cosmos can have an outsized impact. Its discoveries remind us that the universe's history is a story of interconnectedness, where even the faintest lights have shaped the grand tapestry of existence. Remember to like this video and subscribe to our channel for more awesome and informative content like this in future. As JWST continues to explore the distant past, it promises to unravel more mysteries, offering deeper insights into the origins of the universe and our place within